you have a Mac?
I do not have a Mac.
That's fine.
Okay.
Go like that.
All right. So, welcome to the PyTorch workshop. I'm Nate. This is Hamza. Basically, what we're going to do is we're just going to give you an introduction to PyTorch. It's a deep learning framework. You use it instead of TensorFlow. And we're going to tell you about, firstly, why it's good, and then we're going to show you some of the things you can do in it and how you do it and why it's better than TensorFlow. So,
oh yeah, so full disclosure about this slide, I didn't realize we'd be putting up the tiny URL with the link to the GitHub, so I just put it there anyway, but yeah, you have both these links, so I guess just use that one.
It'll, in the README on that GitHub repo, it tells you how to install it, if you would like to install it early while we're going so that you can run the demos later. However, we do have a slide on installation because it is one of the good things about PyTorch, is that installation is easy. Anyway, so who this workshop is for? We're aiming this basically towards people who already know some deep learning, know what deep learning is about, know a little bit of how deep learning frameworks like PyTorch and TensorFlow and all the other ones work. It's supposed to be a ground-up introduction to PyTorch. We are going to go over the basic deep learning things, but very quickly. But maybe you've used TensorFlow before a little bit, maybe you just know the theory. This is basically who this workshop is geared towards. So, basic background. What is a neural network? A neural network is a composition of linear algebraic operations and nonlinear element-wise functions. So these two things are both neural networks. They're just different ways of looking at them, and they're also different neural networks. But the basic idea is you have this way of approximating a function that's just a bunch of linear algebraic operations, matrix multiplies, and nonlinear functions. And everything is nicely differentiable, so you can train it with gradient descent. You can train the values of the weights in the weight matrices with gradient descent. So we want to be able to implement these. And you can implement it yourself from the ground up in NumPy. But it's going to be long and arduous. That was a 189 homework last week, and everybody hated it. So how do we use these frameworks that have been built for us to make this a faster process, make it a faster process to design these and prototype them and run them, because they're very slow to think about, they're very slow to build, and they're very slow to run. And so there are these very large tools that have been built to make it easier. So what we want to do is we want to define this very general computation structure of the neural network. We want it to differentiate for us, because we don't want to do all the chain rule calculations ourselves. We want it to be as general as possible so we can do all sorts of weird things. In that sense, we want it to be modular. We want to be able to reuse modules here and there, so you can build weird recurrent architectures and weird neural GPU type things and transfer learning, so that you can take a module out of one model and put it into another without having to worry about, is it actually going to work? And we want there to be very little boilerplate for common tasks. This is something that a lot of deep learning frameworks actually do suffer from, is that there's a significant amount of boilerplate, because they want it to be as general as possible. They want to really create like an alternative to NumPy, but they also want it to be easy to build these incredibly complicated neural networks. And so boilerplate does heap up pretty quick.
All right. So one of the main differences between PyTorch and TensorFlow is defined by run. And essentially what that is, well, first in order to explain it, let's start with what TensorFlow is. So with TensorFlow, you have this sort of static computation graph, which is, just like a neural network, which you specify in a session. And when you run this you have this session that stores all of these different parameters, and then you have this feed dictionary which feeds in different training samples and their labels as you train your model. So the model isn't run in what you might call a pure Python setting. It's run in this it's run on a site that's abstracted away and is fixed. You can't change it while it's happening because you have to define this whole session for it, but PyTorch doesn't quite work that way. PyTorch is closer to a neural network framework as someone might write it. Like, let's say if they were to extend a 189 assignment, for example, it's pure Python, it's still close to you, and it allows you to sort of change things as you go. You can change your computation graph as you're running it, which is something that we'll actually see in one of our demos later. But the bottom line of what that means is the sort of graph which tells you how to combine your variables, like if you, I guess, go back to this, like how to apply this composition of functions is something that you can do. And then for dynamic inputs, like let's say that you're processing sentences or something else which doesn't necessarily have a fixed input size, this can be a particular advantage for you. So now let's get into some nuts and bolts of sort of how PyTorch works. And the first thing that we're going to want to know is a PyTorch variable. So essentially, when we're training a neural network, what we have to do is we have to know the data that's flowing, obviously, and we also have to know the gradient so that then when we backpropagate and update our weights, we're able to do so with all the appropriate gradients. And we have to know the creator, so that'll tell us sort of what to update, whose gradients are updated from a particular value. So a variable in PyTorch just stores all of these things. And it's derived from a simpler unit called a tensor, which is just a PyTorch version of a NumPy array, which is something that you can like run across GPUs and like integrate in nicer ways than a NumPy array, but it's heavily NumPy based. Oh yeah, and just another point, there aren't placeholders like TensorFlow, because again, going back to the whole session idea, it's like you just have a placeholder that says, okay, as this session goes, we're going to like update things accordingly, so this will become this other thing as determined by the feed dictionary, but then, yeah, we don't have that here. And you can sort of see this computation graph here. It's created on the fly as we do this. So if we look at the example here, so the graph starts here with these variables, and then we have these like matrix multiplies, which then turn into this, and then it's added to become this, and you can see that in the code above.
So this is essentially just a very simple recurrent cell.
Exactly.
So the basic idea here is that when you're running this, you run all this directly. You're not creating placeholders here and then filling them with random numbers. You could, if you had the numbers already, you could put them in directly and it would run this actual code rather than just defining this and then running it.
Mm-hmm. And
hold on a second, I believe there was a, okay, you're right, so we'll go through this one. We'll go through this one and then we'll pause to look at why this is nice, and then we'll go through the TensorFlow one for some contrast.
Yeah, so basically what this code is, for the famous MNIST data set, this is like a convolutional neural network that will be trained to do this. So stepping through this code, basically what we have here is we have this NN module class, which allows us to make a new model based off of existing PyTorch parts. So first, we do some initialization, that's whatever. And now here we have a conv2d, which will have a 1-channel input and then output 10 channels with a kernel size of 5. And then we have another one that goes from 10 to 20 doing the same thing. Then we have some 2-dimensional dropout, and then we have an affine linear layer, which goes from 320 units to 50 units, and another one that goes from 50 to 10. So this is what our model itself will look like, independent of any data. And now, what we have here, we have some data. So our forward method will take in some data x, and then what it's going to do is, so first we're going to apply this conv1 as defined over here to x, and then we're going to do a max pooling, and then we're going to apply a ReLU function, and then we're going to do do another convolution. We're going to do the dropout, and then we're going to do max pooling and ReLU again. View just allows us to change the input size to play nice with dimensions, just standard across like many different things.
Just flattening it.
And then we're going to apply our first fully connected layer, ReLU activation function. And then we're going to apply another dropout, and training equals self.training. That's to make sure to only apply dropout at the right time and not do it at test time. And then another fully connected layer. And then our final softmax activation function. And were you going to say something?
Yeah, one thing that's interesting to note here is just what determines whether you need to put something up here, because you notice we didn't define the ReLUs or the max pools up in the top here. Basically, when you're creating a model this way, and there are simpler ways of creating a model, but this is the general form, what you put in the top is anything that has parameters. And when you do, self.conv1 equals, and then you put something that has parameters there, it'll get added. That's when it gets registered with the model. So anything that has parameters, you put up at the top there.
Although, just to note, that's like good style, but it actually is possible to do like activation functions and other things at the top as well, and you can put them into your model that way, but that's usually not considered like better style. It's better to use this more forward API that takes in the data directly, whereas like you'll notice that with the convolutions, when we initialize them, they're not initialized with data, they're just like our objects, and they store. And another important thing is they store their own weights. We'll see later with TensorFlow that you have to put in your weights manually, which can be more annoying and can help make your code more concise. So these are like first-class objects that, in a sense, know what they are, if that makes sense. And now for training, what we're going to do, so the first thing over here, so model equals net, we're instantiating an instance of the model that we saw on the last slide. If args.CUDA, that's just initializing CUDA if we have it. And then we have like our optimizer, we're setting it to an SGD with like the parameters of the model. And then learning rate, that's just like some boilerplate learning rate that we like passed in earlier. And then momentum, same deal. And now what we do over here is we have this train method, which basically it's only for dropout. It tells us whether, when we apply dropout, are we doing it or not? And if it's train, we do. So then we're just looping over our batches. We're converting our data and labels to CUDA if we can, and then making them PyTorch variables, as we saw on the last slide, so that the gradients can be appropriately done with the model. We're setting the gradient to 0, applying the loss, and then we're doing backward on the loss, and then backward on the weights to backprop it. And then finally, if we've been training for a certain number of epochs, we just preamp the loss, see how we're doing. Pretty standard stuff.
One thing that, do you want to talk about the fact that it's loss? Maybe you can do the define loss here.
Oh yeah. Yeah, that's nice. You can't really do that in TensorFlow. You sort of have to do it separately.
In TensorFlow, when you define your loss function, you put it on top of your model, you have to do it when you define the actual graph. It'll never in a million years allow you to put it in with the rest of the training stuff where it looks like it belongs, because by the time you get to this code, it's already built all the stuff. You're inside the session. You can't add stuff to the model once you're inside the session. So this is one way in which it makes more sense to do it this way, at least in my opinion.
Yeah. And so now...
I think it's my slide. So we just saw how you do in this example in PyTorch. You can see it's pretty nice. We write normal Python code within these subclasses of module. Because it's defined by run, and you aren't building this graph that you will later run, it's a lot more Pythonic. If you need to do something where you have all of these variables that are coming from all these different sources, and you need to combine them in a weird way, and it's not some complicated linear algebra operation, it's just put this one over here and this one over here. It's very Pythonic. You write exactly what you would expect to write in terms of normal Python code. And we have this module.forward. Module.backward is what the auto differentiation is. So when you call loss dot backwards, that's what goes back through the entire graph, back all the way to the input, and computes the gradients. You don't even have to look at it 99% of the time unless you're doing something really weird where you're defining a module subclass and it's doing something that it doesn't know how to compute the gradient for. But nearly everything it does, so you just do module.forward and you don't worry about backward.
And just sort of another thing to actually add to that is, for each of the different units that we saw, like the convolutional layer, the linear layer, that'll each have its own backward defined, just do it appropriately for you when it's supposed to.
It's heavily NumPy inspired, as we said already, and then we really didn't have to write as much code as we did in this slide, because we could have replaced this whole thing with a sequential module. That's something that does TensorFlow have a sequential module now?
No, Keras does.
Keras does, but sequential is basically just instead of writing, instead of even making this a new subclass of module, we would just write sequential and then say this conv2d and then a pool and then a ReLU and then this conv2d and then a pool and then a ReLU. We would just put it all in a list, and so there's a lot less boilerplate if we do it that way. You can't do it that way for complicated models, but for simple ones like this, where it's just apply these operations in sequence, you could do a sequential module, and it's a lot quicker.
All right, and now let's sort of look at TensorFlow. So with TensorFlow, okay, so the first thing to just get what I should say about this code is that some of the code, is just like comments, so it's not as long as you would think, but even still, it's still fairly longer than the PyTorch part. Part of that is because you'll see here we have these TF name scopes, and essentially what those are is later we'll see something called Tensor Board, which allows you to visualize your model. But with TensorFlow, since it's not object-oriented like PyTorch, it's more imperative, and we're in this session, you have to keep track of all of your different parts, like each convolution, ReLU, or whatever, and you have to do that because it'll want those for later, but we don't have to do that in PyTorch because it's object-oriented, and each object knows what it is, it keeps track of everything, so the scope, it'll just take care of that for us. And another thing to see is that we actually have to initialize weights outside and then put those in, as opposed to like you see over here, for example, as opposed to just having the object store them. So that also just saves some code. And here we can see the loss. Again, like Nate said, we have to define it. We can't define it in the function itself. We have to define it outside because it'll be a part of this sort of static computation graph. And finally, we have some training code over here where we have the summary scalar thing for a tensor board. We have our optimization, and then we're going to be applying that. It's somewhat more verbose, and then later there'll be the feed dictionary part of it.
Is that on the next slide, or no? It skips it.
Well, that's just sort of standard boilerplate. Nothing too much, but basically it's just slightly more verbose, and you have to manually feed in your data this way into the session, as opposed to just feeding it into the model directly.
And one thing about that is we don't have it here because it's boilerplate that you have to write for everything. But when you actually do the training, you do it inside a session. And because the computation graph is already created and you're doing it all inside this session, when you see an error, it's a lot less likely to be helpful because you generally don't see as much of your actual code in it, because it's not running through your actual code when it runs the model. It's running through its computation graph. And you can see the general idea, but with PyTorch, if you hit an error, it hits your actual code. It runs it. It runs it verbatim. And so it's a lot more likely to produce helpful error messages if something goes wrong in PyTorch. So installation. This is something that the PyTorch devs really like to brag about, is that it's a lot easier to install. Usually the installation is just conda install -c sumith, because that's the head developer, and then it's PyTorch, Torch Vision, CUDA 80.
Something like that, and then there's also a pip version too.
There's also a pip version, but Torch Vision, which is the thing to download all of the computer vision models that it has, doesn't work with pip. So one thing about this is it's only available on Linux and Mac, but there's one really great thing about it, which is that you don't have to download CUDA yourself. As long as I think it's display drivers are NVIDIA, it will download CUDA for you and install it for you, and you don't have to worry about CUDA or CUDNN or anything like that. It'll download it for you, and the people who develop PyTorch have developed this thing that goes along with it and downloads it all. You don't have to compile it differently to get it to use GPU. You just have to add the extra, make sure this uses CUDA by adding that extra CUDA 80 in the install command. And then this is where the hangups occur, which is that they say this sort of idea, is that the great thing about PyTorch is that it just works. The problem is, occasionally it will actually not work, and when it does, you're a little bit screwed more than you would be in TensorFlow because it works for so many people. But we'll get to that and how exactly that means that you are not able to install it more easily as we go into the next slides. So this is what I was talking about. There are a couple of problems with PyTorch, right? The question then is what's the catch? It's a great framework. Everything makes sense, so much more sense than TensorFlow. What's the problem? Since it's new, it's still in beta, there's a little bit less support. If you get a weird error, you might be the first to get that error. Some of it's borrowed from Torch, so maybe you'll find something where somebody had that problem when they were working with Torch. But in general, you might be the first to get any particular error. There's less code written for it because it's newer. But that gap will close. More and more operations, more and more specific things that you would want to do will get added. Not all researchers are using PyTorch, but a lot of them have switched over. Some are still using TensorFlow. Tensor Board, which we'll see in one of the demos, is not officially supported, but you can install it through a couple of people's sketchy GitHub projects, and it will work, as we'll see. And then it's occasionally, in some cases, it's slower, or it doesn't scale as well. And that's because it's designed for research. It's designed for you to prototype things quickly and run them, rather than make sure that you optimize for everything.
Because again, that sort of goes back to the whole static computation graph idea. It is, like, in many cases, easier to optimize for a static computation graph. So that is something to keep in mind if you need something to really scale to production level. TensorFlow is still probably the best thing to use.
However, you can convert models from PyTorch to other frameworks. This is sometimes. There are a couple of ways of doing it. So if you need something that's really complicated, and so you want to build it in PyTorch, but you need it to scale and run quickly, you can build it in PyTorch and export that model using a number of different ways and put it in TensorFlow or whatever else you need to run it in and run it there. The bottom line is this. If you're doing researchy things, use PyTorch, because all the researchy things are going to be done in PyTorch. It's going to get faster. It's going to be supported a little better. Tensor Board is going to be supported officially in the future. So PyTorch is the way to go for all your researchy purposes, definitely, and maybe some production-y purposes right now.
And so now we're going to be getting to demos, but actually before we do that, does anyone have any questions about anything that we've said so far?
So you guys said that it's not good for production application, right?
Yeah. No.
How, why?
Just because in some cases it is a little bit slower. That's the only thing. It might be slower, it might not scale as well, because it's defined by run and it's designed to make sense rather than to use every possible optimization.
So let's say somebody's writing an Android app, how would they use it?
The way you would perhaps use it is write your model in PyTorch, because it's so much easier to write models in PyTorch, and then convert it over. I don't exactly know what the usual way of doing things of writing deep learning models that are run on Android is.
I mean, I think that usually what you do is you make your model, then you like train it offline, and then you do inference or like run things through to make predictions just like remotely. So there, it's like training time in theory doesn't matter as much, because you'll be training it offline, but then inference time or testing time will matter more.
Yes.
What's a boilerplate?
The boilerplate for PyTorch?
Yeah.
Most of the boilerplate for PyTorch that we'll see is related to loading data. Loading data is always very verbose because there are so many different things you have to handle. After you've already loaded your data, that MNIST example we showed was everything. There's no boilerplate aside from that. That is the entire program. And so there is less boilerplate in the learning itself. But there is still some boilerplate to do with loading data, because there always is.
Are there any visualization tools? Like you said, it's not compatible with Tensor Board. Is there any equivalent?
Well, actually, no. What we said is that Tensor Board isn't officially supported. There are sketchy GitHub projects, one of which we are actually using for one of our demos. So we'll see that. So that is one. I think there are some other equivalents. I don't know what they are right now. But yeah, like you can use Tensor Board in a somewhat sketchy way right now. I think that's the best we can do while it's not officially supported.
And the various other people who are developing their own visualization tools, there are plenty of people doing this now because they realize it's necessary, are in general including PyTorch support when they do that. You'll see people say, we have this new deep learning visualization tool and we support yada 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 TensorFlow, yada yada yada. One of them is PyTorch.
Mm-hmm.
All right. Anything else?
No? All right, let's get
let's go over to this then. I might as well hit escape here and move this over. So I'm going to be pulling up a notebook here. Oops. All right, so we'll talk about the dynamic that you do. All right, so this is actually has two examples in it. One of them is the dynamic net. So we said one of the great things is that you can change the way it works at runtime. You can change the graph fundamentally, and this is pulled shamelessly, almost verbatim, from the Torch tutorials, but we're going to see how it works. After we import all our things, we can see that we're defining this subclass of module called dynamic net. And the way what's going to happen is we just have linear layers, because this is just to demonstrate what a dynamic net is going to look like. And then you can see it says here what it does and how it's dynamic. They'll reuse the middle layer. So they'll I'll just look down here. So dot clamp min equals 0 is just a array loop. And then basically they say put it through the linear, then put it through the middle some number of times, and then put it through the output. And that some number of times is random, and it's randomly generated every time that you run this model. That's something that you can't do in TensorFlow, because it wants to know exactly how many times you run this layer every time you run it, when you create this graph, before you do any running of it at all. And so what we can see is that it'll let you change how many times you run things, even swap in and out different modules in order to do whatever you like. You might ask, why is this useful? It's not really. Maybe you could use this as a weird form of regularization. It seems a little bit regularization-y. But this is just an example to show that you really can do more in PyTorch because you have this dynamic capability. So the way it works is we just define that model, then we define our tensors. Currently, we have something that looks like it looks like a placeholder, even though it isn't. But that's just because that's where we're generating our data. And so we can see 500 times it's going to call the model to find the prediction, and then find the loss, print the loss, and then do zero out the gradients. That's what it does before you. That's what you do before you do the backwards, so that you don't keep changing the gradients. And then it'll set the optimizer to actually run that SUG operation. And so we can see if we run this, it'll start working. And this isn't going to do much because it's entirely random data. But you can see it is running this. If we want some proof that it's running it multiple times, what we can do is we can go up here and actually do something here. We can, I can't see whether I'm doing this correctly. What we can do is we can actually print something in the middle there, which is something that is also weird to do in TensorFlow. So you can see we're printing which iteration we're on. And I'm going to go down here and let's only run it 50 times instead, so that we don't print out a million numbers. And you can see it does change how many times it runs the model. Here it only ran it once, here it runs it 3 times a couple times, once, twice. So it changes how many times it runs the model, and it does it randomly. That's something that you really can't do in TensorFlow. So, on to Hamza next.
Yeah. So now another thing that I want to talk about with PyTorch that's helpful is you can actually, it's a lot easier to make sort of custom extensions. So let's say that you want to take some NumPy or SciPy function and essentially integrate it into your own work. I've had to do this a couple of times. It's much easier. Okay, so full disclosure, first, if you're doing something entirely just based off of standard PyTorch or TensorFlow operations, it's just as easy in both languages. You can just combine them, and since they're standard ops, it'll know how to do the backpropagation for you. But if you want to make your own op, it's a lot easier to do that in PyTorch. You can do it in pure Python using some of the classes that PyTorch has in TensorFlow. Many times you'll actually have to write custom C extensions, which can be a lot more of a pain. So I'm going to walk through an example right now of us doing this. So let's say that I have this SciPy conv2d function. So here we have the forward, where we're just taking our input data and our filter. We're turning them into NumPy arrays. Save for backward, we need both of these results for backward, and the correlate 2D is a SciPy function. So that is something that we imported earlier. So we just take these two things, apply the function, and save these two inputs for backward, and return the tensor, and now we have the backward. Again, since this is something we're defining ourselves, this is why we have to have the backward. Most cases, since backward is just built off of predefined things, it'll just do it for us. So here we're just doing the backprop on that. This is the formula that you have to do, because when you're doing a forward pass with some convolutions, the backward pass will involve some convolutions as well. But as you can see, so long as you know what the backprop formula is, you can do it in pure Python pretty simply and pretty seamlessly, which is nice. And here we actually have this other module now. So what we're just doing, we're initializing the module appropriately, and then we have this other parameter class which takes we just make like a tensor out of like this random size kh by kw, makes it a parameter, that's what the filter will be, and then we can call this function. We're going to have like an instance of it here, and then call it on the input in the filter, and you can see that this standard API call like this works just like any other PyTorch function, because now at this point it is. So that is nice, and then we see that if we run it here, we can, so we can like instantiate it here. We have like the model parameters. We have this variable. We pass it to the module, and here we can see we have a bunch of output that corresponds to what the output will be. So we can see that it is indeed doing what we want. Does anyone have any questions about either of these two demos? Yeah.
So for the dynamic net, how does backpropagation make sense if you're like running through the middle layer of a variable number of times? How is that well defined?
It's still well defined because you could run through the layer. You can think about running through the layer a fixed number of times, right? You take this layer and you run it through it 10 times all the time, right? That's something that TensorFlow does. But you can see that backprop still makes sense when you're running the same layer over and over again with the same weights. This way, it just changes what that is at each iteration. It means that the dynamics of the network will change randomly, but as I said, this isn't necessarily something that you would write directly, although you could use it as some weird kind of regularization technique. It could perhaps work as something like that. But really, this is just to show you can change what your graph does at will at runtime, no matter what, because it doesn't pack it all away beforehand. That's one of the benefits of the define by run, and the second one is another of the benefits of the define by run, which is that if you needed to do something where you defined the backward function yourself, where you computed the gradients yourself, if you tried to do that in TensorFlow, a lot of times you would have to write it in C. And I don't know C. I would not want to do that. So PyTorch is great because if you need to do something weird, like use a SciPy function directly, here we just used convolution, which we could have done already. But if you need to do something weird like this, you can do it all in Python without worry. And again, that does make it a little bit slower because it doesn't get to box it all away and optimize it. But it makes a lot more sense.
Any other questions? Yeah.
Never mind. I don't know what that is.
Okay.
Anything else?
All
Before
right.
we move on to the next ones?
Yeah, let's do the nearest neighbors one.
Nearest neighbors. All right. I'll pull this back from over here. Oops. All right, let's get on. 10 more seconds.
All right, just a couple more seconds there, folks. Yeah.
Can you explain the zero weight gradients again? What is?
So basically what that does is when you run PyTorch and you run your optimizer, it'll keep track of all the gradients that you've accumulated, and you want to zero them out so that you don't end up using gradients multiple times, and you only need to be using them once. Yeah.
Basically, when you run backward, it adds to the grad spot in the variable, and so you reset them all to 0 between passes. That way, it doesn't have to worry about whether it's in the same backward iteration in order to do something like where it runs through the same element twice for the same, where there's a split ahead of it or something like that. All right. nearest neighbor layer. So how many of you read Chris Olah's blog or have read some stuff from his blog? This is the guy who did visualizing MNIST and the nearest neighbor layers and stuff like that.
And you have the LSTM one
Yeah.
and convolution network explained. Yeah, those.
He's done a lot of great stuff on understanding deep learning and visualizing deep learning. So one of the things he did was he noted that the way we currently do things is we take our inputs, and what we try to do is we try to define this computation graph where it disentangles the manifolds, right? So there's this manifold in high dimensional space of this is the manifold of all 5s, and this is the manifold of all 3s, right? And this this incredibly high dimensional space that contains all images that are 28 by 28. And we try to define these operations that bend these manifolds until they are linearly separable in this lower dimensional space, or maybe higher dimensional space. And what he said was, that's kind of weird. And it is kind of weird, because maybe that's not a natural thing to want our models to be able to do. Maybe linear separability, which is a pretty strong constraint, is too strong a constraint. And so he said, why don't we do something a little bit more theoretically nice and make what he called a nearest neighbor layer, which is something where instead of, at the very end of your network, instead of just doing linear separability with like one last linear layer, what you do is you figure out in this space how close is your one image that you're trying to figure out whether it's a 0 or a 1 or whatever, how close is it to all the other zeros that you found in this space? How close is it to all the other 1s? That's the general idea of nearest neighbor layers. So I looked at this, I thought it was cool, I thought it was a very theoretically interesting approach, and I decided to change it a little bit. And you'll see what I've done. So we run this, we see CUDA is available. I'm not going to use it, but it is. And this is really the meat of the module, is this dist invert. Basically what it does is it just takes your variable and another variable and figures out what is 1 over the distance between them. And we can see we have these tensors here, the distance between them is 5, and so it'll tell us that 1 of the distance between them is 0.2. Here's a use of the sequential module that I talked about earlier. Instead of writing that slightly longer thing where we had to declare the conv2d registered with a module, declare another one, declare all these convolutional layers and register them with the module so that their parameters could be recorded, we just put everything into a sequential module. And that way it's less boilerplate. If you really do just want to feed one thing into the next, into the next, into the next, and you already know all of the things work out, all of the dimensions are right, everything, you can just do this, and it's very simple. So these are the early layers of the network. Before I go into the next one, we're going to start doing the
boilerplate MNIST.
The boilerplate that I was talking about earlier that is the necessary for loading the MNIST data. So up at the top here, we imported this thing called Torch Vision, and Torch Vision will just download data sets for you. So it's downloading MNIST, and some other things. It's downloading MNIST, it's doing one for train and one for test. And let's see, do we have, I'm going to temporary failure name resolution because I'm not connected to the internet. So I could either connect to the internet and do this, or I could go over and do it and do this elsewhere, where I already have the data downloaded. For you guys, as long as you're connected to the internet, this should work. That is what the name resolution error is. I'm just not connected to the internet. But it seems like it's not connecting, so 10-second break while I go over and go over into the other folders where the data is already on. While we're doing this, does anybody have any questions?
Yeah.
Curious, what's the level of difficulty if you say spin up an EC2 instance on Amazon Web Services and try to use the GPU on that instance with PyTorch? Is that relatively easy compared to doing that with TensorFlow?
Let's see. I don't have too much experience with that sort of thing, actually. Yeah, sure.
Yeah, so if you look for AMI, most likely that like a deep learning AMI, you'll probably have both PyTorch and TensorFlow installed. We will actually be release a AMI for machine learning at Berkeley that has both of them installed. So that means you just need to like specify that you want to use this AMI and then you have both.
I did look at some other pre-built AMIs specifically for TensorFlow, but then I was reading through the reviews for them, and they got progressively worse as it got more recent. It was like they were good from like last spring.
So I just installed them like yesterday. So,
All right, so I ran it over here and it magically worked, even though I'm not connected to the internet because I already downloaded a few hours ago. So we don't have to worry about that now. So basically what we're going to be doing is I'm just doing this so that we can see some of the, this is I think also copied from a tutorial, but we're just doing this so we can see some of the MNIST images, and we can. Here are some MNIST images. And then here is the way that I changed Chris Ola's original idea. In his idea, what he said was the distance that you find is, here's something, we want to know if it's a 0. Find the other things in the mini batch that we know are zeros and compare it to them. And that'll give you your distance. I thought, instead of doing that, maybe we should think about how could we get like a platonic ideal of a 0, or a platonic ideal of a 1, or something like that, and compare the distances to these platonic ideals of each of the digits, so that you can, it seemed a little bit theoretically nicer to me. And also, it's less expensive than comparing it to lots and lots of images all the time, because you only compare it to 1. So let's see. What I have in the nearest neighbor, the nearest neighbor folder that I put in the repo is these platonic _4.npy, platonic _0.npy, etc. Those are just stored numpy arrays that contain these. So while I was doing this over the summer, when I was just experimenting with these nearest neighbor layers, I searched through the MNIST dataset and found these 9 images, which I said these are like the platonic ideals, or nearest I could find to it, of these digits. And so these are what we're going to be comparing to in our latent space towards the end of the module, in order to see which one which one is closest to. So this one is fairly simple. It's just take that early thing with all the cons in it, the convolutional layers in it, and then flatten the output and put it through a couple of linear. This is basically finishing up our feature extractor, which is most of the model. And then this is the finished thing. So what we can see is we're going to keep an array of the hidden, the output of the last hidden layer after you run it through the feature extractor for all of the platonic ideals of the images. Then we're going to find it for our input as well, then we're just going to basically find, all right, for everything in our mini batch and for all of these Platonic images, what's the distance between them? And then we're going to do softmax on that. So let's see here. If we run this, we can see here's what you will get if you print a model in PyTorch. So we have, you can see it really does capture the idea of it's modular, because we have this feature extractor followed by the dist invert, and in this early, within the feature extractor, we have the early and then the linears. So it's very nice and modular. And if we go down to the next one, I'm going to do this. We can see that we've successfully converted it to variables. And then we're going to do the optimizer and the WAS, and we can start training it. I'm not going to, because it's going to take a very long time to train. But I did that long time to train earlier, so I'm just going to load the model. This is loading the trained model. There is some wonkiness with loading in PyTorch, because there are two different methods, one for loading the model and one for loading just the structure of the model, and one for loading a model with weights. This is the one where we're loading a model with weights. And then we can try and run this on our test set, and we can see what the accuracy is. We're going to see that the accuracy is not great, because I didn't train this for very long, and I didn't change the initialization at all, and I didn't change the hyperparameters at all. It's really just a proof of concept. But once this finishes, we can then, there we go, it's 95% accurate. And then we're going to go through some more of the test images. I did not. N10 is what I'm looking for here. Right, here's a test image, it's 7. That's what it is, it's a 7. And then we can do this, and we can see here's the output of the dist invert before it gets put into the softmax for this image compared to the Platonic images. So you can see here at the 7th one, 7, 8, 9, it has the highest value because it is the closest to 7 out of all the Platonic images that we have. So that's how this nearest neighbor layer thing works. The reason we included this as a demo is just to sort of show you what a normal model with some twists looks like in PyTorch, because that's something that you're going to be writing a lot if you do research with PyTorch. And one of the interesting things is that it really does make a lot of sense what you write when you write something weird, where you have to store things in arrays and then put them into the things. You know, you can do list comprehensions. It's very, very Pythonic, and it makes a lot of sense. It doesn't always in TensorFlow and in the other frameworks. So there is the nearest neighbor layer, and I'm going to. Firstly, does anybody have any questions on this? Why you would do something like this? Anything like that? All right, cool. So I'm going to close out of this. We already did this one.
Yeah, now for the last demo.
Now for the last one is Tensor Board.
So we're going to be switching over projectors now.
Okay. I'll do that. Oh, goodness. I'll press this thing. I think this is the thing.
Yeah. Yeah, so now we're going to be going over one of the sketchy GitHub projects that you can use for PyTorch to actually do this.
It's not finding it.
Oh. Yeah. Because for this one, you just need to plug in this. There we go. All right. So.
You want to put that up here?
Yeah. So the example that we're going to be going over is the same dynamic net that we went over last time, just so then we can focus on the important Tensor Board stuff. So the only difference in import is here we import something called a summary writer. So that's basically going to be responsible for logging all of the important metrics that we want to keep track of. So we instantiate an instance of that here. The initialization is exactly the same as is the forward, because the only difference here really is we're going to be changing things when we actually run our model on the loss. So you can see right here for name parameter and model.name parameters, we're going to be adding a histogram of each name, and we're going to be cloning the parameter, getting the numpy version of the data. So this .data converts the PyTorch variable and just extracts the data part, turns that to numpy. And one nice thing to note here is that, again, unlike with TensorFlow, we don't have to do the scope thing, because again, it's like we already know the names of each of the parameters that we're going to want to be getting the summary statistics of. So this is really a very short thing to do. So, and now what we're going to be doing is here we're actually going to be running the model on an example, getting the output, and then we're going to add a graph of the model at that point, because again, since PyTorch, and in particular this example shows, we can do dynamic graphs. So in order to figure out what it's actually going to be when we're running Tensor Board, we have to get a specific instance of it like this. We can't just we can't just rely on the scopes like TensorFlow does. So if we run this, we'll see that it's going to be exactly the same. But then what we can do is we can do this. So if we look in the command in the folder where I'm running it, we see that we have this runs folder. So these are just different instances of me running it. You'll see that this one at 9:07 and 48 seconds is the one that I just did. So we can run Tensor Board by this command, tensorboard --log dir runs. Actually, what I'm just going to do is I'm going to get rid of all the runs, run it again, and then show you guys that, just so that then we don't have like different runs cluttering it up. Alright. Alright. So now we're going to do this. And then soon we'll be getting URL. So yeah, so Tensor Board has been started, so we can navigate to it here, and you can see that we have Tensor Board again. So we have this graph, which represents an example of the model, and it's written in the same sort of format as the computation graph that we showed earlier in PyTorch. So we have like this input linear, we're doing a transpose, doing an add multiplication, doing some more add multiplications and transposes, so we can get a nice graph like this. And but this isn't really the main sort of reason that people use Tensor Board. You use it more for distribution. So you can see that we have input linear, the bias, and you can see how that changes throughout our runs. You can see the actual weight values, the middle linear bias, the middle linear weight, output linear bias, and output linear weight. And we can also go to histograms and see that, so you can see how it changes over time, you know, oftentimes this can be useful if you want to see, for example, you might have like the vanishing gradient problem when training neural nets. Your gradients just aren't flowing, and you can sort of see if that's happening, where it's happening across this. So this provides a nice way of doing that, and so that, you know, takes away what would be an advantage to TensorFlow and sort of equals the playing field in that regard. It's pretty simple, doesn't require too much boilerplate code, but you know, it is still a sketchy GitHub project and not an official thing. So for example, if you were to go to the official PyTorch forums, you can't get help there with that. You'd have to like go directly to the GitHub repo. So does anyone have any questions about this? Either the code that I actually used to train it, or like I guess just any of the Tensor Board specific stuff that I added here, or the Tensor Board layout here. Alright, well if no one else has any questions, then I think this is the end of the workshop.
That's it. Does anybody have any questions overall? Since this is the last demo we have, we don't have any slides after the demos. If not, I think that's it. Oh yeah?
I'm still trying to construct it in my mind.
That's fine. Anyone else? Yes.
Where do you guys get the data for all these?
So the dynamic net was just trained on random data because it was really just showing that yes, you could in fact construct this kind of a thing. For the nearest neighbor layers where we actually did MNIST, Torch Vision, which is something that you can download which is something you can install at the same time if you install it through Conda, Torch Vision will just download a bunch of vision data sets for you. MNIST, ImageNet, CFAR 10 and 100, I think, these sorts of things. So Torch Vision was what we used to get the MNIST data there. It has a whole different interface for data loaders if you have your own data stored in your own format, but we didn't show that here. But it does have that infrastructure built up as well. But the main focus is not on that because that doesn't necessarily differ too much from framework to framework.
So download pre-trained models also and list of.
Yeah, you can. You can download, like for example, like ResNet, AlexNet, a bunch of others. So that's very much something that's built into PyTorch.
And the model format is like Torch.
Say again?
The model file, is that coming from Torch or?
The model file, there's still some clearing up they need to do about this. When I loaded in the model, the pre-trained model for the one that I was doing, for the nearest neighbor layer, it was just something that I had saved previously from the exact same notebook, so it worked well. I think it was, I think it might have been pickle format, just normal Python stuff. I don't, you know, it varies, and that's one of the ways in which PyTorch is still in beta, is that there are still a couple of conflicting ways of downloading and running models, but since that's something that so many people need to do so much, there's a lot of support on that, there's a lot of documentation on it, etc.
Have you looked into, there's this new thing called Onyx?
Yeah, that's actually one of the things that we were talking about when it came to like transferring models over. Like we mentioned that you can write in PyTorch transfer to like, let's say Cafe 2 or something like that. Yeah, Onyx is how you would do that.
Yeah, I'm not fully sure about what it is either. But from what I gathered was it's a specification to represent these operators.
Mm-hmm.
And my understanding is that it does work with PyTorch, and that you can use it to its full extent, but I haven't looked into it personally. Anything else? All right, well, I think that's the end of the workshop. Then we'll be up here if you want to come up and ask other questions, or specific questions, anything like that.
But yeah, if not, then thank you everyone for coming. Hope you learned something today. Is this one yours?
Yeah, this one's fine. I didn't really work with the Tensor Board.
Oh, that's because
Not
that's something that
specifically.
has to do with
Hamza
updating Tensor Board.
I don't know.
Let me see.
There's,
I got
think
this.
there's someone in this room.
I got this error once before when I was running it. I don't remember what
If you
the
look
it
like
is
I
actually.
can add. Hamza,
Yo,
anything here? Someone talking about this now?
let's see. Phil, that guy in the blue shirt who answered the AWS question would probably be the best person to talk to. I helped facilitate it like a semester ago. Hold on, yeah, let me see what the error is again.
Really beginner I mean, we can take the MLab data science decal. We put out, it's at the end of every semester and the beginning of the next week, we put out information about that.
Yeah. Yeah, applications will come out like beginning of next semester.
Aside from that, what do you recommend under the
Yeah, no, I think
beginning and machine learning?
Yeah, no, I think the data science decal is like a good source for that.
And since it's such a hot topic and everybody's so, you can look up a bunch of, courses, online courses and stuff, or a couple of them. You can find this.
Shoot, my internet's not really.
Ask about what you're doing.